All right, so we are learning the concept of colligative properties and freezing point depression. So, colligative property is a property. There are many different types of properties or traits that we talk about in chemistry. Freezing point is a property, it is a physical property. And a colligative property is any property that depends on the number of particles. How many particles are there? It doesn't matter what the type of the particle is, it simply depends on the number of particles. And we're looking at a specific colligative property, freezing point, and we're going to call it freezing point depression. The reason that we can make ice cream is because we manipulate the freezing point of both of the water, or rather the ice that we use to chill and freeze the ice cream. The reason that we can make our roads safer, or attempt to make them safer when it's icy weather outside, is because of freezing point depression. And the reason that we can maintain our car and the water in the radiator won't freeze in the winter when it gets below freezing outside is because of freezing point depression. We're going to make ice cream, and you have an assignment that deals with your radiator and antifreeze, so you have to learn freezing point depression. So, pure water or any other pure solvent, whatever the freezing point of that solvent is, for instance, at pure water, it freezes at 0 degrees Celsius or 32 degrees Fahrenheit. If you add a solute to it, the solute can be a liquid, the solute can be a solute can even be a gas. You can dissolve gas in water. But if you add something to pure water, such as salt or sugar or ethylene glycol, antifreeze, it's going to lower the freezing point. Now it happens to also raise the boiling point, but we're not all that interested in that right now. We're interested in lowering the freezing point. So pure solvents, they have a freezing point. Pure solvent plus something dissolved in it, going to have a lower freezing point. And how low that goes, how low it can go, depends on the number of particles. It does not depend on the type of particles. So that is a colligative property, and we are studying freezing point depression. So we have our unit, the mole, which deals with the number of particles. Okay. This is a sugar molecule. I'm just going to refer to that as a square. This is a salt molecule. I'm just going to refer to that as a square also. So whether you have a sugar molecule or a salt molecule, here you have some crystals of, I think that's the sugar, no, that's the salt, and this is the sugar. So each of those crystals is made up of gazillions and gazillions and trillions of molecules. And because it's in the solid phase, they're not moving around too much. They're vibrating, but they're not moving and flowing like a liquid. And you have these things here which keep them sort of in a solid structure. These are called intermolecular forces. We're not going to really deal with those right now. We'll deal with them later. But it's simply some type of a force between molecules, and it keeps them in a solid crystal structure. Now, if you dissolve salt or sugar in water, different things happen because salt behaves differently than sugar in water. So here we have a salt crystal, and each of those salt crystals has got some salt molecules. Salt molecules is made up of two things, right? Sodium and chlorine. Now, when you dissolve something in water, water molecules are going to surround particles and sort of carry them away from the crystal. And therefore, it becomes something that we can no longer see because it's dissolved. Now, in salt's case, water molecules will surround each atom in the molecule and carry them off. So one salt molecule will actually give us two particles when dissolved. Again, colligative properties deal with the number of particles. The type of particle is unimportant. However, if you have a sugar crystal, there's our sugar crystal there. These things are held in place by those intermolecular forces and so forth. And then we've got our water molecules here. When you dissolve sugar into water, the water molecules are going to surround a sugar molecule, but they are not going to break apart the sugar molecule. Here, they break apart the salt molecule. Here, because of the properties of sugar and things similar to it, they do not break apart the molecule. The molecule remains intact. So technically, one molecule of sugar is going to give us one particle when it's dissolved. When the water molecules carry off that sugar molecule, it doesn't break apart, so you still have one particle. And that's the difference between dissociation and dissolving. Dissociation is a special kind of dissolving. To dissociate yourself from something or someone means to break completely free. So, in other words, if you had 4 sodium chloride molecules, 4 salt molecules, and you dissolve them, you would get 8 particles. If this broke apart into 2 and so forth, 4 of these would give you 8 particles because there are 2 atoms. 4 molecules times 2 atoms gives you 8 particles. Likewise, if you had 4 gazillion molecules, each one with 2 atoms, you would get 8 gazillion particles when it's dissolved. That makes sense? 4 moles gives you 8 gazillion particles because each molecule has 2 atoms. 8 gazillion sodium chloride molecules would give you 16 gazillion particles because each molecule has 2 atoms. 8 gazillion molecules, 2 atoms each, 16 gazillion particles, or 16 moles. Sugar. If you have 4 sugar molecules and you dissolve those things into water, you're still only going to get 4 sugar molecules, even though each sugar molecule has this formula, which is 45 atoms. Those atoms do not break apart. This is dissolving. This is dissociation. Another example. Let's say that you have calcium chloride. Well, this has 3 atoms, 2 there and 1 there. 3 molecules, 1, 2, 3, times 3 atoms means you get 9 particles. If you had 3 gazillion molecules, 3 atoms each one, you would get 9 gazillion particles. This is a different compound than sugar. I think that's aldehyde. If you had 3 of these molecules, or 3 gazillion of them, they don't break apart. So when it's dissolved, you're still going to have 3 gazillion particles. And that's it.